All right, so permutations. Wow, you have plenty of storage space there, don't you?
I can bring all my stuff.
You might just decide that that's like the right way to go from here on out, right? It's like,
I actually
I mean, like extra clothes, lunch, books, just throw it in, right? And you don't even have to like try to pack it.
And he can write it in.
Yeah, you can like put a whole human being in there, so, you know.
I did fit Alex in here.
Oh, right. And if you don't have time to come home, you can just like sleep in it.
Exactly.
But, yeah, okay, so permutations. The basic idea behind a permutation is this: you've got a sequence of objects, and sequence means order. Okay, in mathematics, when you say sequence, it means that you have some items in a particular order, which is different from collection. In mathematics, when you say the word collection, you mean that order makes no difference, typically. So we've got a sequence, and then we reorder that sequence. Okay, but we do so in such a way that we make sure to include every element that was previously there, and we don't introduce any new elements. Okay, so we just basically reorder a sequence of objects that we already had. Like, for instance, this. Let's say that I had a sequence of objects. Oops. I'll just go in alphabetical order. There's absolutely no need for that. I mean, you can use whatever objects you like. It's commonly the case that letters are used, so I'll use letters. You don't have to put them in alphabetical order. Any order will do, but it's easiest to start with alphabetical. Okay, so let's say that we have the 6 letters A, B, C, D, E, F, and then let's say that we reorder them. Okay, so A, B, C, D, E, F is the original order, and then let's reorder them. So give me the first letter, and the B, and then E, and then F, and then C, D. It has to be D, right? Because we've already used B. So it'll be D. And then what haven't we used? Okay, there we go. So we've reordered. And notice we've done this to produce a genuine permutation. It's the same letters, okay, and the same number of occurrences of each letter. Just the order has changed. So, side note here. You don't have to change the order in a permutation. It's perfectly acceptable to leave them all as they are and still call that a permutation. Actually, it is an important kind of permutation when you begin to build like mathematical systems with permutations as can be done. Do you know what a mathematician would call that permutation?
Identity.
That's exactly right. There's only one word in mathematics for what that can be called. Okay, when you do an operation with some object and it doesn't take you anywhere, it doesn't change anything, that's always the identity. Like the additive identity is 0. The multiplicative identity is 1. I don't know if it's universally true, but for all the most important mathematical processes, operations that mathematicians study, there is an identity element, and its existence is absolutely essential. Okay, so the identity permutation, nothing changes, but this is not it. Okay, this is not the identity permutation. So here's an example of a permutation. Simple idea, of course, right? Now let's talk about how it is that we can represent permutations. And we'll get to a really clever way that mathematicians often represent permutations that shows something really important about their structure. Okay, so here's one way that one might represent the permutation, not that clever way that we'll get to, but correct. Okay, so here's one way to do it. Notice that B after the permutation occupies the position that was occupied by A. So let's say it like this: A maps to B. Okay, and you can see that first A and then directly below B. And then B maps to E, and then C maps to, this is simple stuff, right? What does C map to? F, and then D maps to C, and then E maps to D, and then finally F maps to A. That's exactly right. Now let me pause for a moment. My purpose here is really to talk about the mathematics, but let me mention the Python for just a moment. This group of functions, these 5 functions about permutations, it's in the dictionaries chapter, okay? And that's a very strong hint about what I think the best data structure is that you should use to represent a permutation, and that's a dictionary, okay? I don't tell you that. Instead, I talk about the mathematician's notation for permutations that I'll introduce in a moment. I don't say anything about dictionaries. But of course, the information given in a permutation has to be represented in Python somehow or another. You need some data structure to represent that. Dictionaries, I think, are the way to go. And I think that if you represent the permutation in the way in which I've done with this arrow symbolism, where we have A maps to B and so on, I think the dictionary structure becomes clear, right? So when you say A maps to B, a very easy natural translation into Python is that, okay, so that's element of a dictionary in which the key is A and the value is B. And then in that same dictionary, you would have a key of B and a value of E. Okay, so that dictionary shows what maps to what. Another side note here. Have you realized the close similarity between dictionaries and functions? Actually, dictionaries are a variety of function. I mean, not in the sort of Python sense where you create a function with def and so on, but rather in the sort of conceptual sense of what a function is, the mathematical sense. That is where a function like takes a value and then returns a unique value. Okay, that's determined solely by the input value and depends on nothing else. That's what dictionaries do, right? The input is like the key and the output is like the associated value. And like when you do a dictionary lookup, that is dictionary name and then key and square brackets after the dictionary name, that's like a function call, okay? And the value of that is like the function return value, okay? I mean, there's a very close similarity between dictionaries and functions. In fact, probably the best way to think of a dictionary, it's just a function where you explicitly specify the outputs for the given inputs. Okay, you don't like have to do some computation and figure out what the output is. You just say in the dictionary, if the input is this, the output is that. And if the input is this, the output is that. Those are the key value pairs. Okay, so it's a dictionary in which you explicitly specify the outputs for all the given inputs. And then, again, permutations are naturally represented as dictionaries. And then let me draw the natural conclusion here. Permutations are functions, okay, in that mathematical sense. Because what does a permutation do? A permutation takes an arrangement of letters, permutes it in accordance with a rule, the permutation rule that I give there with the arrows in this case, and then produces a rearrangement of those objects. Okay, so there's input, output, and computation, which is rearrangement. Oh, and let me show you this. Okay, so I applied our permutation to A, B, C, D, E, F. We got B, E, F, C, D, A. You could apply that permutation again to B, E, F, C, D, A. Good, let's do it. Okay, so to what does B map? Again, B maps to E. So there we go. E maps to D, F maps to A, C maps to F, and D maps to C, and A maps to B. It is the same permutation rule applied to that second sequence. This is iteration, isn't it? You can iterate the permutation. Now, here's something cool. I think that I will take time tomorrow to prove that this is true. I know I've mentioned it to a few people in class. That if I continue to apply this permutation rule given by those 6 arrow statements, if I continue to apply it to each new output, I'll eventually get back to the identity permutation. That is the original A, B, C, D, E, F. Okay? I'll get back there, which is very cool. This is always true. If you have a permutation rule that tells you how to change the order of a set of objects, if you continue to apply it again and again and again, you will eventually get back to the original configuration. Yeah.
You get back there like after every single combination, or is that some random point?
It can't be random, right? Because every point is like completely deterministic, right? The permutation rule tells you at every stage exactly how you have to rearrange, right? There's nothing random about it. So it should be that there's a quite deterministic answer, right, to how many times you have to do this. And that's a really superb question. As a matter of fact, one of the functions that you have to write is called the cycle length function, and what it does is it takes a permutation and asks how many times does that permutation have to be applied to give back the original configuration. And one way to do it is just apply it again and again and again, right? Just like in a while loop until you get back to where you started. But a really great question would be, okay, so that's like the brute force technique. You just do it, right? And then watch what happens and then stop when you get back to where you started. A really good question is, could you predict how many that would take and not have to actually do it? And the answer is absolutely. You can do it. And I might talk about that a little bit tomorrow. And that's going to be one of the brilliant features of the notation that I'm about to show you, that this notation allows you to get to that quickly. Okay. All right. So we know what a permutation is. We know one way to specify a permutation, like the A maps to B, B maps to E, and so on. That example, which, of course, can naturally be represented as a dictionary. Let me show you another way. Okay. And this is going to be so-called cycle notation. And this is that bit of, I think, brilliant mathematics that I wanted to show you. And all the functions are about this. Okay, all the functions that I wish you to write, those 5 permutation functions, they're about cycle notation. Okay, so I'm going to take that sequence of 6 arrow statements and convert it into cycle notation. Here's how I'm going to do it. Open parenthesis and then A. Okay, by the time we're done, you'll recognize the significance of all this. Why do I start with A? Why not? I don't have to. I can start with any letter. Just so long as every letter gets used at some point along the way. I start with A because, alphabetical order. But if you wanted to start with, like, D, that would be fine as well. Okay, so A. To what does A map? B. So I write the B after the A. Okay, to what does B map? B. Okay, to what does E map? D. To what does D map? C. And to what does C map? F. And to what does F map? I close parentheses. As soon as we map back to the original element, we close parentheses, and that means that the final element maps to the initial element. Okay, that's what this symbolism means. This is kind of a curious permutation. Okay, because I didn't have to stop at any point and start up again. Okay, it's one chunk. I sort of hoped that it wouldn't be, but it is. Okay. So let me give you another example. Okay, I tell you what, let's go in the opposite direction. Okay, just to make sure that you understand the cycle notation. So I'm going to actually use 2 sets of parentheses. Okay, so I'm going to go A and then B and then perhaps D, and then I'm going to do this in such a way that I don't have any repetition of letters. Repetition is possible. One of the functions I wish you to write takes a permutation specified with this kind of cycle notation that has multiple occurrences of a letter, compresses it down so that it does not. I'll talk about that tomorrow. So I'll make sure that I don't do this now. So what do I want C to map to? You tell me. So C to F. And then I tell you what, I'll leave it just like that. And I'll actually make a point. So I've got an A, B, C. I've got the D. I don't have an E. And you might wonder, well, isn't this an issue? Why don't I have an E in there? Well, maybe there was no E in the original sequence. Okay, but here's something else that you should understand as well. If a permutation leaves an item in the same place, that letter name is typically not given in cycle notation. Okay, it's just left out. It's left out. Now, let me show you what this particular term permutation specified in cycle notation would do to a sequence of letters. So A, B, C, D, E, F. So let's see what's going to happen to that. Okay, so here's what the notation means again. B follows A. So that means that A maps to B. Okay, so there it is. A maps to B. To what does B map? No, look at the cycle notation. So what comes after the, or maybe you said it right and I didn't hear it right. What follows the B? C. Okay. B follows A. That is A maps to B. D follows B. That is B maps to D. Oh, and then we're at the end of a chunk. I wanted you to see a permutation in cycle notation with more than one chunk. Okay. So we're at the end of the chunk when we hit D. That means we map back to the original element. So D maps to A. So there it is. Immediately under D will be the A. So let's now jump to the second chunk. So to what does C map? F. And then to what does F map? F is the end of that chunk. And if you're at the end of a chunk, you always map back to the original one. So F maps to C. And then if there is a letter in your sequence that is nowhere in the permutation, that means that it maps to itself. So E maps to E. Okay, so that's another way that a permutation could be specified. And if one were to do it in that column notation, it would be just like this, right? A maps to B, and then B maps to D, and then D maps back to A, and then C maps to F, and F maps to C, right? So those are equivalent, ultimately. Now, there's something really cool about this. I'll just say this a little bit. My purpose today was to get you familiar with cycle notation. But cycle notation, in this simplest form, in this compressed form, where we don't have multiple occurrences of any letter in the cycle, okay, in the sequence of cycles, right there, circled, it tells me something very curious, something very important about the permutation. What it's telling me is this, is that one portion of the sequence is separated off from another portion of the sequence. That is, the letters in the ABD positions, they trade positions, okay? But they never trade positions with anything in the CF chunk, okay? And then in the CF chunk, well, those two trade positions as we apply the permutation, but nothing in the CF chunk ever trades positions with anything in the ABD chunk. So this has shown us something very important about the permutation. It's allowed us to like sort of factor the permutation, as it were, into two pieces, okay? That together give the whole permutation. Now, let's see if you can figure something out. There was a really good question a moment ago about like length, right? Like how often do you have to apply the permutation so that you get back to where you started? Well, let's see. How about just the CF chunk, okay? How many times do you have to apply that to get the two letters back to where they started? Twice, because the first time you apply it, C maps to F and F maps to C, and then the next time you apply it, it undoes that, right? I don't know, like just look at this particular example. So let's say that we've got this very simple permutation and cycle notation, and let's say that we're going to apply it to the sequence AB. So what does A map to? B. What does B map to? A. Let's do it again. What does A map to? B. What does B map to? A. We're back to where we started. 2 total cycles. Okay, so how about, okay, so that's for CF. 2 repetitions bring the C and F position letters back to where they started. How about the first ABD? How many times would that have to be applied to get the letters that it moves around back into the same position? 3 times. Its length. So how many times would we have to apply the whole 2-part permutation? The product of the 2, which is 6, which is extraordinary, isn't it? So that means this: if you can factor a permutation into the cycle type notation where none of the cycles overlap, that is, you don't have the repetition of a letter, then you can tell immediately what the cycle length is, which is freaking cool. It's great. Now, there's one other question that I'm not going to address today. It's entirely acceptable, okay, so last little piece here, it's entirely acceptable to write a permutation like this, where you have, well, lots of chunks, 3 different chunks in this case, and where you have a letter that occurs in more than one chunk, okay? That's perfectly well defined what that means, okay? However, that can be recast, rewritten as a permutation in which no letter does occur twice, okay? That's what I call the compressed perm function that you're supposed to write. And what's really, really cool about that is that, well, that structure that I was talking about before, it's like the chunks of the permutation that don't interact with one another, they're revealed if you put it into that compressed form. So tomorrow I'll talk about like what that final permutation and cycle notation means, and how it is one could hand compress it down to a permutation that doesn't have multiple occurrences of a letter. Because of course, you can't write the code unless you can execute the algorithm by hand. So I'll show you how to hand execute the algorithm next time, and it's actually super cool. Okay, so that's it. That's enough for today. And then tomorrow I'll talk